Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing OSPF, where we will review OSPF concepts, configurations, and troubleshooting in Junos. In this lesson, we'll be going into the building blocks of OSPF in detail. Here, we'll be reviewing the types of messages that OSPF speaking routers generate and their formats. OSPF is a Layer 4 protocol. Recall from your JNCIA studies that Internet Protocol, or IP, lives at Layer 3 of the OSI model and is used by OSPF. This means that OSPF packets are encapsulated in an IP packet header. In the following slides of this lesson, we'll review the 5 different types of messages OSPF uses, their purposes and data fields, along with their bitwise packet formats in depth. Understanding the types of messages that OSPF uses is key to understanding how the protocol operates to reliably and quickly propagate network reachability information throughout the network. So, let's take a look at the packet types. As we see in the diagram here, OSPF uses 5 different message types: the hello packet, the database description packet or DBD packet, the link state request or LSR packet, the link state update or LSU, and the link state acknowledgement or LSAC. Each of these packets share a common OSPF header that's included at the beginning of each. The header includes the router ID, or RID, which is a unique identifier for the OSPF speaking router in the network. The router ID takes the form of an IPv4 address and is 32 bits in length. Typically, the RID is the same as the router's loopback address. The OSPF header also includes the area ID for the interface. In OSPF, each interface on a router is assigned to an area. As we discussed briefly in a previous lesson, the area concept in OSPF is used for scalability and controls the size of the LSDB or link state database that each router maintains. A router can only form an adjacency or neighborship with another router whose interface is in the same area. To form an adjacency or neighborship means for the device to agree to forward network reachability information to one another. They will periodically send messages to each other to remind each other that they are still alive, and will engage in a database synchronization process to ensure they both have identical LSDBs. It's worth noting that the term adjacency or neighborship in this context can be used interchangeably. As mentioned, this process is used to establish a relationship between network devices which allows them to exchange network reachability information. The network reachability information that's exchanged is contained in link state advertisements, or LSAs. You may notice that in the diagram below, that link state advertisements are not one of the 5 packet types in OSPF. This is because LSAs are a building block contained within the LSU packet type. An LSU can carry one or more LSAs. The exchange of routing information, or network reachability information, is made reliable through this mechanism here. An OSPF speaking router will first request a particular LSA from another, which are transmitted to the requester in an LSU, and received LSAs are then acknowledged using an LSAC packet. Each of these packet types have various fields contained, which make the packet type fulfill a particular purpose in OSPF. Let's take a look and review each one in detail. However, first, let's take a closer look at the common OSPF header. Here, we have the OSPF header that's included with all OSPF packets. The first 4 octets include the version, which the common version is version 2 for IPv4, the packet type field, and packet length. The length field is particularly important, considering how an LSU can contain a variable number of LSAs within. The RID, or router ID, is 32 bits, or 4 octets in length. As mentioned before, it takes the form of an IPv4 address, since it is 32 bits in length. The area ID can also be expressed in the form of an IPv4 address, since it too is a 32-bit field in the header. The following 32 bits contain the checksum field for error checking and AU type field, or authentication type. Only 3 values for the authentication are defined, with the remaining values reserved. The 3 values are 0, which is null or no authentication, 1, which is simple password authentication, and 2, which is cryptographic authentication. The remaining values are reserved by the IANA for future use, as defined in RFC 2328. The following 64 bits are used for the authentication information, depending on the authentication type selected in the previous field. Next, let's take a look at the OSPF hello packet. The OSPF hello packet is the initial and primary packet used by OSPF to establish and maintain neighbor relationships. These hello packets are encapsulated in multicast IP packets. They have a destination multicast IP address of 224.0.0.5, which is the reserved, well-known multicast address for all OSPF-speaking routers. In the diagram below, we see the fields included in the OSPF hello packet. The fields marked with an asterisk are required to match between OSPF-speaking routers for a neighbor relationship to form. The network mask is the prefix length of the network that the advertising interface is configured for. The hello interval is in seconds and is the frequency at which the advertising router will send hello packets, which are also used as a keep-alive mechanism in OSPF. The dead interval is the amount of time that the advertising router will wait between receiving hello packets before it will consider a neighbor router to be dead. The concept of a neighbor being dead means that the neighbor relationship is deleted, and all LSAs received from that router are deleted from the LSDB. The options field is used for a router to advertise its capabilities. When used in hello packets, the options field allows a router to reject a neighbor because of a capability mismatch. The router priority, designated router, and backup designated router fields refer to a concept we'll cover in a future lesson. Designated routers and backup designated routers are routers which hold a special role in a broadcast network containing multiple OSPF-speaking routers and are used to generally minimize the amount of unnecessary traffic due to flooding of LSAs. The election of this role is performed using the router priority field. Finally, the OSPF hello packet includes a list of all of the router IDs that the originating router considers to be neighbors. This is also the field used to determine when a neighborship is formed. If a hello packet is received which contains the local router's RID in the neighbors field, then it knows that the originating router agrees with the fields which must match to form a neighbor relationship. Now, let's take a quick look at the bitwise packet format of the hello packet before we move on. Type 1 OSPF packets are the hello packets. This should not be confused with the LSA types that we'll see in a later lesson. As we see here, the network mask is 32 bits in length, as expected. The hello interval is 16 bits. Options are 8 bits of flags, and the router priority is a decimal number, which is 8 bits in length, representing a decimal from 0 to 255. The dead interval, which is the amount of time the advertising router will wait between receiving hello packets from a neighboring router before declaring it dead, is 32 bits in length. The dead interval is typically set to 4 times the hello interval. Being that it is always a larger number than the hello interval, the field must be a larger field than the hello interval. Next, we see that the designated router and backup designated router are included in the hello packet. These fields are populated with the interface IP address of each, or are set to all zeros if none exists yet, or the link does not require the election of one. Finally, we've got a list of the neighbors that the advertising router is aware of. This is a variable length field, since a variable number of routers may be included in the hello packet. Each entry is populated with the router ID of each neighbor known to the advertising router. This is the primary mechanism used for establishing neighbor relationships between OSPF-speaking routers. When a receiving router sees its own router ID in an advertising router's packet, it knows that the advertising router agrees with the fields that must match for an adjacency to be formed. We'll go into the neighbor relationship formation process in more detail in a future lesson. For now, let's move on to the next OSPF packet type, the database descriptor packet. The database descriptor packets are the Type 2 OSPF packet and contain 3 primary fields. The OSPF header that's included with all OSPF packet types, a sequence number to ensure reliable delivery, and a link state advertisement header for each LSA contained in the advertising router's LSDB. There are a few flags as well and options, which we'll review in the bitwise format shortly. The database description packet are used during the adjacency formation process so that the routers may synchronize their LSDBs. Recall that for a single area of OSPF to operate correctly, the link state databases of all OSPF-speaking routers in the area must be identical. The DBD packet plays a key role in this process by allowing routers to describe to one another what LSAs are contained in their database without needing to exchange the full details of each one. During the neighbor relationship formation process, when the routers are ready to exchange database description packets, the router with the highest router ID is the one to begin the exchange, and will set the initial sequence number on the DBD packet. So, let's review the bitwise format of the DBD packet. As we see in the first 32 bits of the packet, after the OSPF header that's included with all packet types, we have the interface MTU, 8 bits for describing optional capabilities, and 3 flags. The interface MTU, or maximum transmission unit, is, of course, the maximum frame size that may be received by the advertising router on this interface. This MTU must match on both routers, which are trying to form a neighbor relationship. If they do not match, then the OSPF neighbor relationship will not proceed past this point, and therefore will not fully establish. The optional capabilities flags won't be covered in detail by the JNCIS ENT, so it's sufficient to know that these fields are present. The next 5 bits are always set to 0 in OSPF version 2, with the next 3 bits representing flags that are important to the DBD exchange process. The I flag seen here is also called the init flag. When this is set to 1, it indicates to the receiving router that this is the first DD packet being sent in the sequence. Otherwise, it is set to 0. The next flag is the more bit. When set to 1, this flag indicates that this is not the last DBD packet in the sequence. There are more DBD packets to be sent. Finally, the last flag is the MS flag, or the master-slave flag. When set to 1, it indicates that the sending router is the master in the DBD exchange. This would be the router with the highest RID. The following fields are the sequence number, which is initially set by the master router, and then the LSA headers used to describe the LSDB of the sending router. each header if 32 bits in length, and either all headers will be included in a single DBD packet, or all which can fit into the interface MTU, and therefore additional will be sent if needed. Once each router has the information from the DBD packets, essentially the description of each other's LSDB, they will proceed with requesting the LSAs that are not present in the local router's LSDB so that they may be synchronized. The next packet type is the link state request packet, or the LSR. The LSR packet is sent when a router determines that its LSDB is out of date or stale. This can be in response to an LSA header seen in a DBD packet that the local router doesn't have in its own LSDB. This could also be used in response to an LSA aging out from the LSDB, and the router is requesting an updated copy of the LSA from a neighboring router. The LSR packet contains 4 fields: the OSPF header that's included with all packets, the link state type, the link state ID, which is the same as the LSA header, and the advertising router ID. These 3 fields uniquely identify an LSA. However, it does not specify which version of the LSA is being requested. It's understood that an LSR is always requesting the most recent version of an LSA. A separate LSR is sent for every LSA that the sending router is requesting a copy of. Let's take a look at the bitwise format of this packet type. The LSR packet is one of the simpler packet types. Outside of the standard OSPF header, the LSR only contains 3 fields that are 32 bits each: the link state type, link state ID, and advertising router. In response to an LSR, a receiving router will send LSU packets which contain the requested LSAs. Let's review that packet type next. The link state update packet, or LSU packet, is really the foundation of the protocol's network reachability information propagation system. The LSU carries LSAs, plain and simple. An LSU packet can carry 1 or multiple LSAs. These packets are always destined for 224.0.0.5 or 224.0.0.6, representing the all OSPF routers and all OSPF designated routers, well-known multicast addresses, respectively. The packet format of the LSU is similarly simple to the LSR. It simply contains a field that gives the number of LSAs that the LSU is transmitting, and then includes the full details of each LSA. So let's see what this looks like at the raw bits. You might remember me mentioning that the purpose of LSUs are to transmit LSAs, though you may not have expected that this is the only purpose of the LSU. Here, we can see that truly the only information contained within an LSU packet are LSAs. The first 32 bits of the packet are used to describe the number of LSAs contained in the LSU, and the remainder of the packet is simply used to transmit the details of the LSAs. Now we've covered the database synchronization process almost completely. We've learned that the router with the highest RID starts the database synchronization process, and that DBD packets are used to share with the neighboring router what LSAs are contained within their LSDBs. Once the routers receive the full database descriptions, they then send LSRs to request the LSAs which are missing from the local router's LSDB. And the requested LSAs are transmitted in LSUs. Once the LSAs are transmitted, in order for the transmission to be reliable, we need to acknowledge their receipt. This allows for the transmitting router to validate the receipt of the LSAs and retransmit any that were not received for whatever reason. This leads us into our final OSPF packet type, which is the link state acknowledgement, or LSAC packet. As we just described, the LSAC packet is used to acknowledge successful receipt of LSAs. A single LSAC packet can acknowledge receipt of one or multiple LSAs. The LSAC is the simplest OSPF packet, which only contains the OSPF header and the LSA header for the LSAs that the LSAC is acknowledging. Let's see what this looks like in the bitwise diagram. So, you might believe me now when I said that this is the simplest packet. Other than the OSPF header that is included with all OSPF packet types, we simply have the LSA headers for each LSA that is being acknowledged. That's the last of the OSPF packet types. In the following lessons, we'll take a deep dive into how OSPF works and how it uses each of these packet types to propagate routing information throughout a network in a scalable and reliable fashion. I appreciate you sticking with me through this lesson. I hope that this lesson has been informative for you, and I would like to thank you for viewing.